Hi there, welcome to our channel where we talk about traffic operations in practice. The overall intent of this video series is to reduce the learning curve for students and entry-level engineers by providing them free and high-quality learning materials in the field of traffic operations, including highway safety and travel demand modeling. The majority of content in this work is written by Professor Jiangling. My name is Amit Kumar Singh. I'm one of the contributor of this work. I'm a licensed engineer in the state of Texas. I received my bachelor's from IIT Bombay in India and my master's from UT Austin in US. Other three contributors of this work are Priyanshu Singh, who works in the field of artificial intelligence, Nidhi Kumari, who has a background in computer science and is a programmer, and Namrata Kumari. She has a background in electrical engineering and currently she is working as data scientist. Now let's get to the main content. In previous video, we looked at how to set up the model and run the sub-area analysis once we receive the travel demand model from MPOs. And in next two videos, we will look at model calibration. Model calibration is a manual, iterative process. It's a little bit tedious kind of process where we are trying to match the TDM output with the existing counts for different peaks. So let's say AM peak period, PM peak period, and daily. So model model class calibration is kind of subjective. It's kind of non-interesting kind of topic, but this is where as a travel demand modeler, as the user side of travel demand modeler, I should say, spend majority of our time. So let's say I'm working on a travel demand forecasting project. So the most time we spend is on report writing. So report writing can easily take between let's say 40% to 60% of our budget. So report writing takes a lot of time. There is a lot of thought process that goes to write a travel demand report. Out of the remaining budget, um, let's say model calibration takes on an average 30%. So now if the report writing is 50%, model calibration is 30%, then we are left with around 20% to play with other models, code alternatives, and do many other things. So model calibration is a big part of the effort we try to put on traffic forecasting project. So if we are looking at an engineer who is working on travel demand forecasting, chances are either he's working on report writing or he's working on model calibration. So let's get started with the model calibration. We will have two videos to it and we will move slowly to describe the processes with a little bit depth and examples. So the process of adjusting travel demand model so that output link flow can match the collected count is called model calibration, which is typically done for when the model is developed. The model calibration is done for base year. However, by the time we get to use the model, is already interim year. So most of the time we end up doing the calibration based on interim year output or interim year TDM model. So we run the interim year TDM, get the output from Transcat and try to see what we can do to match the counts. With the availability of new data sources, uh, especially the OD matrices, TDM models are now also been calibrated to match the OD trip tables. So in interim year output, earlier we were trying to match only counts, but because of big data analytics, we are also now trying to match the OD trip table. However, it should be noted that the OD trip table we obtain from the last data sources such as streetlight and other sources only uses a small sample of traffic data, and most of the time the OD table which we get from big data sources may be unreliable. So it's something to remember that TDM model in itself gives an OD. TDM model has its own OD. Then we are trying to match a let's say observed OD, but this is not like 100% observed. This is an sample estimated OD we got. So if these two ODs are uh, very different from each other, then no matter what adjustment we do to the TDM, we will probably not end up with the observed OD. So it's kind of very tricky to change the TDM if the TDM OD is not kind of in alignment with the observed OD. So it's very important to know the limitation of observed OD and in practicality, because the observed ODs are based on sample data, what we do is we give more priority to matching count. So matching count is given more priority. So first we try to fit the counts, and if possible then we try to fit the observed ODs, because observed ODs are usually sample based. If the observed ODs are actual ODs with 100% sample sampling, then we would match the observed OD more because that's more accurate. But usually the observed ODs are collected from different platforms, and they just use 6 to 10% of actual data to calculate the observed ODs. So unless we are very confident that observed OD is highly reliable and the sample size is pretty big, the TDM is given priority to match the counts first, and if and only if uh, the counts are matching, then we try to match the observed OD if it's all possible, which in most cases is not. So it's kind of a something to remember going forward, because there are a lot of new platforms that are throwing a lot of existing OD data, and the challenge has always been those OD data has not been reliable. So figuring out the reliability of the new OD data, figuring out how good the TDM OD is, uh, then we can have a better handle on calibration. There is a big presentation I've created on how to handle the counts, TDM OD and observed OD together, depending on how reliable the observed OD is and how reliable the TDM OD is, given that the counts are 100% reliable. So this is a kind of a little bit complex iterative process. We'll not go in depth. I have prepared some presentations and I have went through the thought process. However, it's important to remember that observed OD are sample based, and we must declare its reliability before actually trying to fit it. So that's a side discussion to calibration, because observed ODs are becoming a big deal now. So that's a side discussion to remember. In traditional approaches, the model coding error correction. So majority of TDM calibration is just fixing errors and assumptions. So TDM errors, TDM model calibration is fixing errors. There are a lot of them in the TDM model, and fixing approximations. Like we looked at approximations earlier, given the large number of data set, a lot of approximations and assumptions are made during the development of a travel demand model, which is good for a large regional network. But when we are looking at a small region, let's say 5-mile corridor, and we are just focused on that 5-mile corridor and area around it, then those approximations can be um, can lead to wrong results. So most of the TDM effort is around errors and approximations. So let's look at the first approximation, which is link speed. Uh, in previous videos, we have looked at the link speed. Link speed is what defines the link travel time. So the traffic assignment primarily depends on link travel time, which is a function of link speed. Free flow speed or free flow travel time or free flow speed is an important parameter that defines the link travel time. So one thing to remember here is one of the most important parameters in the travel demand model uh, is basically link travel time. All the parameters that affects the link travel time is going to affect all the network flows and everything. So as mentioned in previous videos, free flow link speeds in TDMs are generated based on lookup table. So what happens is we have a long list of links. We have usually, let's say, 30,000 links. We cannot go and code the link speed for all of them one by one. So in previous videos we have discussed that what we use is a lookup table, and the lookup table looks like this. If we move a little bit up, in previous videos we have seen this lookup table like this. So there is a capacity estimation, alpha and beta, and then there is a free flow estimation here, free flow speed. This estimation is generally based on the functional class of the roadway and the area type. However, when we are working on a project, this approximation fails pretty badly. Let me explain it. Since this is such a common and very important thing, let me explain a little bit more in depth on what does this approximation do and why it fails. So let's say we are working on a project and we have this freeway. So we have this blue freeway, then we have some arterial going like this, just these three. So what approximation does is based on the area type. Let's say we are working in urban area consistently for the study area, and functional class for this blue line is freeway, and functional class for this green lines are arterial. Now what lookup table does is, as long as the area type and functional class, let's say major arterial, so there are like 19 or 20 different functional class, not only 6 and 7. So minor arterial, major divided arterial, major undivided arterial, but let's say all three of them has same functional class. So what this what the approximation does is, as long as the functional class of the road is same, the free flow speed on these links will be exactly the same. So let's say the speed limit on this road is 45 miles per hour, on this link is 30 miles per hour, and this link 35 miles per hour, irrespective of whatever the speed limit is there, because we are doing a big approximation, and from the lookup table, let's say the speed came out to be 40 miles per hour. This 40 miles per hour will be assigned to this one, and this one. This is a very big approximation when we are focused on a small region, and this is one of the most common mistake, most common sources of error that creeps in travel demand model. So before looking into how to fix this error, let's look at one of the example that is provided here. So in this example, 3.15, let's say 3000 vehicles are going from this direction, this origin to this destination, and they have three different routes. One is straight route with 45 miles per hour, which is seems to be a fastest route. Then we have one long route with 35 miles per hour, and then we have another, this red route with 40 miles per hour. Now intuition will tell us that more people will use the direct route. So out of 3000 vehicles, majority of people will choose the shortest route until the travel time on this one goes up, and then people would divert to the other route. So let's say the distribution of volume on these three routes, based on our intuition or actually observed, is 1300 in the center one because that's the fastest, and then 800 here and 950 here. So fastest, second fastest, and slowest. Now what TDM assignment does throughout the system is it looks at the functional class of these roads and area type, just two parameters. Uh, or depending on how the model is built, it can look up more parameters, but it's generally based on a lookup table. So it looks up in a lookup table and try to figure out the capacity. Capacity is generally dictated by like a generic capacity with number of lanes. So let's say all three roadway types have same functional class, same number of lanes, which gives them the same capacity and same area type. So besides speed, the other parameters affecting travel time, which is capacity, alpha and beta, are same for three roadways. So let's say these three roadway are identical to each other in every aspect besides the speed limit. So what travel demand model would do is it will assume that the speed on this link, speed on this link, and speed on this link is equal, and let's assume that the length of these three roads are equal, even though it's drawn like this one is a little bit longer. Let's assume that the length is almost equivalent, almost equal. Let's say these are like longer routes of 10 miles. So if these are 10 miles, so let's say this is 10 mile, this is 10.5, this is 10.2 or something like that. So length is pretty long. Let's say the length is pretty long, so the length of these three are almost equal. So what travel demand model will do is it will assign a speed to this one from the lookup table, then and assign a speed to this one based on lookup table, and then assign a speed to this one based on lookup table. So let's say the based on the lookup table, the speed is around 40 miles per hour. So this one will become 40 miles per hour, this one will become 40, and this one will become 40. Since the speed and travel times are same and all the characteristics are almost same, the travel demand model will assign one third here, one third here, and one third here. And when we are trying to compare it with the reality, instead of 1000, instead of 1300, we got 1000 vehicles. So we are missing like 300. We are missing 300 vehicles from this roadway. From here we are 50 vehicles short, and here we are 200 vehicles short. This 200 vehicle sort is approximately 20% error. This 300 extra vehicle extra is about 30% error. So as we can see, even by changing the speeds using lookup table, even by a little bit amount can creep in a big link errors. So that's the first biggest source of error. Biggest source of error is the travel time and travel speed cannot be manually coded. We cannot go in field and figure out the speed limit. One of the best indicator of free flow speed is the speed limit. So instead of using lookup table, if somehow we go in field and figure out the speed limits and we code those speed limits, then the model may perform a little bit better. However, the speeds are typically defined based on the lookup tables. Speed limit is still not completely accurate, but it will be much better improvement over wheel lookup table which we currently use. So we have speed and capacity lookup. So capacity is also handled in the same way, whereas capacity between the similar roadways may be different. So speed lookup table gives gives one kind of crude estimation on the link speed, and that crude estimation messes up. The crude estimation looks good when we are working on entire MPO model. Let's say we are working for NCT cog and we are working with a big network. Then the small diversion here and there will be like small fluctuation in a bigger system, and it will not matter as much. Whereas when we are looking at the smaller projects, then the small fluctuations pile up pretty big, and the percentage error they introduce is pretty high. So in my experience, based on link speed, we can expect the error between 10% to somewhere 30% error, just because the link speed are used as the lookup table. Now here it says that traffic flow assignment errors due to link speeding coding errors is quite routine. To resolve this issue, the link speed are checked and corrected at every stage at an early stage of the network checks. So if we have wrong speed coded and we are trying to calibrate, no matter how many iterations we do, we will end up in a cycle, because if the speeds are not coded correctly, then vehicles will transfer to some other routes onto which we are not expecting higher demand. So this needs to be corrected at very early stage before we start to do hit and trial on the calibration. There are some links that will have link speed errors, and the link flow on the parallel roadway would mismatch due to count. So the one way to detect whether the speed is coded incorrectly, let's say we have 500 links in our project. So let's say we have 500 links in our project, and we went ahead and fixed all the link speeds. However, we missed few of them. So if we miss some of them, what would happen is, let's say we missed one of these links, then the flow on this link and flow on any parallel routes, so flow on this one and flow on any parallel route will mismatch. So if the flow on the center link is higher, then there will be less vehicles here, and if the flow on the center one is lower, then there will be more vehicle on the alternate route. So by looking at parallel routes, we can try to guess whether there is an error happening because of the link speed or travel time. So that's the first approximation, first source of error, where the travel time between two nodes uh, are kind of unrealistically coded, or they need to be fine-tuned for the projects. So that's the calibration step one. The first we go and fix all the link speeds. It's very important. Again, if we do not fix the link speed, we may end up in a long vicious cycle of changing many parameters and not ending up with a calibrated network. So it's very important to fix this error at a very early stage. The next biggest source of error is Centroid and CCs. This one is interesting one. So the location of a Centroid should be coded as the geometric mean of the trip generated by development in a TAZ. Typically what we think is, let's say, as we have discussed earlier, each TAZ can have only one Centroid, because the TAZ layer trip generated is transferred to the roadway layer by unique IDs. So we can have only one Centroid. So what we can do is, let's say there are one development here with one driveway at this location, one driveway at this location, and this development 3 is pretty big and it has two driveways. Now what we try to do is we try to draw the centroids such that we are balancing out all the development. So when I'm looking at Google Maps, let's say some developments here, some here, some here, then a travel demand modeler would draw the, while developing the model, they would draw the centroid in the middle, which kind of equivalent balances out all three. Let's say development 1 is not there and 2 is not there, then we will just draw the centroid here. And let's say development 2 and 3 are there and 1 is not there, then we will just draw the centroid here. So that's the general idea on how to draw the centroids. Let me reload this real quick. Okay, so what happens is, let's say these three developments are in play and we draw the centroids here. As soon as the centroids are done and this centroid connectors, they kind of represents this driveway. So driveway, this driveway, since we are playing with blue color, I will just use red. So another driveway, another driveway, another driveway. So the centroids kind of needs to represent some of these driveways. So there is one connection point here. Let's say somebody wants to go from this TAZ in the north direction. They're not gonna, take this and go up. They're probably gonna take this centroid. So all the driveway access are kind of drawn through the centroids like this. Now what happens is, depending on the position of the centroids, the length of connector changes. For example, in this one, let's say we have one development here, less developments here, less developments here, then we move the centroid in this area. And when we are trying to assign the volume to this centroid, which is given in this example, let's say in this is observed floor where 500 vehicles are going from this development and coming like this, 50 trips are going like this, and 100 trips are going like this. Now since we are forced to combine three development by one centroid, uh, this centroid needs to move downwards. So instead of putting the centroid here, we have to put it towards this this development, because there are more developments here. So now there are three routes available. One is this, one is this, and one is this. The way traffic assignment works is gonna assign the flow. If we want to reach the common destination, a traffic assignment is gonna assign the most of the flows to this shorter connector, just because this is like the shortest travel time. So in reality this was 500, but the trip assigned to this route is 620. So depending on how this centroids and connectors are drawn, the vehicles that are getting loaded on the system. So for example, uh, let's say there are some vehicles which are going from this direction to here. Then in this case they will be using this route, or they might be using this route. However, uh, let's say this is a residential area with a, you know, with several students living in here, and there are public schools here. So there will be a lot of drivers in morning going to school. However, because we are replacing the individual development with a center point, it will always pick the shortest path. So it will most likely not choose this path, it will just take this path and this path. So these small fine details on the location of centroids, how the connectors are drawn, where they are drawn, kind of plays a bigger role when we are working at a small zoomed in level. So again, they do not play a big role when we are looking at a big macro level. So when MPOs develop their model, they calibrate it on a bigger level, and at a bigger level everything looks nice, and we as a consultant uh, or we as engineers get to work on those models. But when we zoomed in, then all these small uh, errors or small intricacy comes in play. So Centroid, because Centroid and uh, CCs are all over the network. So let's say we are working with let's say 50 zones, then we are looking at 50 centroids, and let's say 2 connectors per zone at least. So we are looking at 100, more than 100 connectors. Now we need to check whether one of the connector at each of the zones, whether they are getting over assigned or under assigned, or whether they are correctly representing the development within the area. Because the travel demand model does not have this information, so we have to look at Google Earth and figure out what the look at the Google Earth and the traffic count on the roadway to figure out how the trip should have been distributed, and then we try to figure out how the trip is getting distributed, and then we move these centroids appropriately such that the counts are matching, and the number of trips that are assigned to each CCs is kind of what we are expecting. So one way to fix the issue that is pointed here is to move this centroid from this location, and we want to kind of produce some vehicles that goes through this connector. So we want to decrease this number, we want to increase this number, and we want to increase this flow. So what we can do is we can move it a little bit here. Let me reload this one more time. What we can do is we can move this let me change the color. We can move this centroid little bit towards where we want the flow to move. So we want the flow to move towards 20, so we will move the centroid here. What we can also do is we can reduce this connector length. So we can draw the connector here, so bring this connector connection point a little bit down. Even though driveway is here, we just need to connect it here, and we need to connect this one here. One important point to remember here is typically when we receive the TDM models, these connectors are drawn at the location or driveway. So when we receive the TDM model, we typically have one connector which connects here, one connector which connects here, and one connector which connects here. Let's say this one is already captured in this. However, when we are working on project, we have to change the position of these centroids, and we also have to change the position of these connectors where they are connecting to match the reality. So we might end up moving this centroid here, and we might change this connector which is connecting here to, let me show. So we might change the location of connector here, then we might connect one here, we might connect another one, let's say here, and we might connect another one here. So the location where this connectors connects only can be determined when we looked at zoomed in level. So when we get the travel demand model, we do not have that information. So when we work on actually running the model at zoomed in level, then we have to make this adjustment. So I would highly recommend to read through all the text that kind of goes through what I have described and some more information. Uh, but all in all, that's the idea. So first, what we do is we fix the link flows. We fix the links flows by first looking at how the link travel times are defined. There are mostly errors in link speeds or free flow speeds. So first we fix the link flows, then we fix the TAZs, Centroid and connector positions, because this affect where the trips are assigned in the vicinity of the study area. So it will affect the trip assigned onto this neighborhood roads. It will, in a bigger scheme of things, when we are looking at more than 100 zones, this would not matter because ultimately they will converge and they will go where they want to go. However, in when we are looking at zoomed in level, where we are trying to figure out where this may be an intersection of interest, or where this location may be an intersection of interest, and if all of our volume is going through here, then we will have less volume at our intersection of interest. So when we are looking at zoomed in level for our project, it's important to get all this correct. So this is the second approximation that is frequently wrong, and we have to fix it. So possible solution of fixing are, first we move the centroids, and then we also correct the connectors. So initially the connectors were connecting where the driveways are located. This is how most of the models are coded. The models are kind of geometric eyeballing on these developments and then connecting them on where the driveways are. However, in practice, we changed the connection point from where those driveways are to the more realistic way where the flows are matching based on the flows. So we changed the connector size such that the flows are matching, and we do not give too much importance on where those driveways are. Now, if these developments are significant enough, the another option would be to split those TAZs. So this TAZs, because we get it from census data, we try to maintain it as it is. But if there are too many variation in the development, what we can do is we can cut the development into two halves. So the lower one will become 1 TAZ, upper one will become 1 TAZ. Now we can figure out where these strips are going, and where we can figure out where these strips are going. So we can attach it like this maybe. So splitting a TAZ is a very tedious and very difficult process. Splitting TAZs. So if a TAZ consists of various isolated development, it might become necessary to split it into smaller TAZs. Splitting TAZ into smaller TAZ is a very complex task, as the attributes of smaller TAZs needs to be calculated based on the original TAZs, and these calculations are not easy. And then additionally, new TAZs would have their own Centroid and CCs. So now we have two different TAZs, and then we have two different Centroids and CCs. So like I mentioned earlier, each TAZ, let's say the ID of TAZ is 200. Then if we draw a Centroid here, its ID must also be 200. So if we split it into half, then let's say the ID for top Centroid is 201, and let's say the ID for bottom, if I can draw it well. Okay, so the ID for the top part, let's say it's a triangle like this, is 201, and the ID for the bottom TAZ is, let's say, 202. Now we need to delete the previous centroid nodes and recreate two new centroids with connectors, and we need to assign the ID as this centroid ID as 201, and this ID as 202, let's say. Now overwriting an ID within a transcade of all of the nodes is a very complex process. Is very difficult to overwrite the nodes. From my experience, there are temporary IDs we have to create, then create a file with the override, and then we have to do it like 3-4 times before it actually changes. So it's not easy. It can take you, if you are not familiar with how to overwrite IDs, it can easily take you multiple days just to split the TSAs. So this is the least recommended and should be used as last resort. When we are done with everything and we cannot calibrate, we can split the TSAs, but this is highly challenging and not recommended way. After looking at two big sources of error, which are link speed coding, Centroid location coding, and connectors length coding, and connectors position, which is directly related to where the length of the connector. Let's look at some more sources of error. So another source of error is planned projects or discrepancy in coding the projects itself. We usually check for the planned projects for all travel demand models. So the planned projects are coded in travel demand model based on the information provided at the time of model development. Like we have seen in previous videos, by the time the model starts developing, let's say we have base year, and by the time engineers get to use those models, there can be a lag of 3 to 4 years easily. So what we typically do is we first compile a list of projects that are gonna be there in interim and future. So first we compile a list of projects from our local MPOs, cities, counties, and clients. So we get a bunch of projects. Now we divide these projects into two categories. One is transportation projects, which is directly related to transportation network, and another is land development projects, which is like traffic impact analysis mostly, and which are gonna impact the TSEs. So we are looking at list of projects. The land development projects are going to impact our TSEs. Mostly land development projects are given in the form of TIAs. We receive a bunch of PDFs with a bunch of TIAs. And then a list of transportation projects usually come from like regional plans. Now what we do is we try to figure out whether this has been coded correctly. So let's look at them one by one. First, let's look at the easy one, which is the transportation project. The way to detect the errors in transportation project is first we go and select all the links. So select link, in which the link attribute, so select links with attribute in the base year is not equal to attribute in the future year. So this can be many attributes. This can be number of lanes, this can be capacity, this can be speed, this can be many things. So if a link attribute has changed between the base year and future year, let's say link does not exist in base year, which is 0, and link does exist in future year, which is 1, then what it means is there are some projects that are planned to improve this link or remove this link. So it means we must have a accounting for where this link change is coming from. So it can go in two ways. The first one is we figure out all the links that are not similar between base and future year. The future year can be interim or the horizon. So between base and future year, we looked at attributes that are different, mostly capacity, number of lanes, or whether the link exists in both years, and see whether there are projects in the plans that can account for these changes. So links that are different between base year and horizons year are selected using select feature, select formula in Transcad. The difference in link attributes are compared against the list of planned projects. So what we have is from MPOs, we have all the list of roadway project, usually greater than 200. we have a long list of projects, and then we figure out the links and then compare them one by one. So let's say a link is flagged for number of lanes which were in existing. Let's say there were 3 lanes, and in future number of lanes became 4. So what we want to do is, so this is existing, or let's call it base, and this is called future. So let's say we saw a link where number of lane is changing from 3 to 4. Then we will go and compare it against the list and try to see whether that roadway exists with the planned project, and see whether this change is justified. In the similar way, we try to figure out all the projects that are applicable to us. So out of all the projects that are given to us, only a subset of projects are applicable to our study area. So we select the projects that are applicable to our study area and try to see whether all of them are accounted in the network coding. If there is a mismatch between the list of planned project and the list of projects coded in Transcad, we can easily fix them by changing the attributes and replacing the attributes. And then we have to make a note of those changes. So usually those goes in a calibration report on what changes we are making to the TDM model. So we make those changes very easily, but we kind of keep a track of what changes we are making, and those are reported in the final report. Contrary to transportation projects, land development projects are a little bit difficult to change, but they are still very easy to kind of figure out whether they have been coded correctly or not. So let's say we received a bunch of TIS. Usually we get the land development project information by something called TIS, which we discussed in the second video of this chapter. So let's say this is TIA1, this is TIA2, which is applicable for our study area, and we have bunch of TIS. Somewhere between 5 to 15 TIS is what we receive in most of the projects. So let's say we have TIA 15. Now what we do is we try to figure out estimate the growth based on this TIA. So we look at the small region where the TIA is done. Let's say this is a zone. So we try to see how much growth this TIA is predicting, and see whether this growth is accounted for in the land in the zones or not. So first we need to figure out how much growth is accounted within the TAZ within the model. So the first thing we do is to calculate the growth rate for population and employment within each TAZ. So let's say this is my one TAZ, this is TAZ number 2. They do not need to be square or rectangle, but just for simplicity I'm drawing like this. So let's say these are my 6 TAZs. So first we look at what is the population growth, and Transcat can give a very nice color. So we can look hundreds of TAZ by color based on the growth rate. So it's easy on eyes to figure it out compared to what I'm trying to draw here. So this is not that difficult. In Transcat we can play with colors and represent different growths with different colors. So let's say the growth here is 2%. We are looking at linear. Let's say here 4%. Let's say here 6%. And 3%, some random number, 5%, and let's say 7%. So this is the growth we are getting from the TAZs. So what we did is we look at existing TAZ, we looked at the future TAZ and compare them to calculate this is TDM growth, TDM TAZ growths, TAZ growth rate. This is population growth rate. We can do the exact same thing for employment. Usually we do not look only at population. Whenever we are looking at population, we always also look at employment. And let's say some percentage here similar to population, we calculated these percentages. Now what we can do is, based on this TIS, we can figure out how much growth we are expecting in the area on top of the background growth. So the TIS would have the background growth, and TIS will also have information on the additional trips that are getting generated. So we can take a guess based on this TIS on how much growth we are expecting and try to see whether this growth are accounted for in this TAZs or not. Let's say we are this TIS says there is going to be a lot of development and this growth is not accounted for in the TAZs. So what we can do is we can keep in mind that okay, there are going to be new developments and this TAZ is not accounted for. So when we are developing our final numbers, we can go on the higher side when we are trying to adjust the numbers. So compared to the roadway network, where we can fix the roadway network very easily by just deleting and substituting the values, the TAZs are difficult to adjust because the growth is coming from population and employment. We cannot change the population and employment that easily compared to the roadway attributes. So here, if the growth rate within the TAZ does not accurately reflect the planned development, then the TAZ attribute needs to be changed, carefully changed. Correction related to coding issues of planned projects. This by planned projects here we mean land development projects, are challenging to fix. Engineers should be careful in attempting to change TAZ related parameters manually. So typically we keep a note of whether these TIAs are accounted for in the zones or not, but we do not touch the attributes that easily unless it's like absolutely necessary. We just keep a note of it, and when we are finally processing the volumes, we adjust it there. Or we try to make sure these things are accounted for at a later stage. So to recap, what we do in plant project, it will get a list of projects from MPO and we divide it into two lists. One is the roadway projects. The second list of projects are land development projects, which are usually TIS. Then out of this long list, we filter out all the projects that are relevant to our study area. A client usually do not give us a list of projects that is relevant to our study area, so that's our job to filter out the projects and not miss one. Then we try to figure out the projects in our study area between TIS and this roadway projects, whether they are accounted for. So if the roadway projects are not accounted for, then we change the transportation system and make a note of it and kind of mention it in the report. However, if a TIA is not coded properly, then we do not go and change the TIS attribute. Those are really challenging to kind of change. So what we do is we make a note of it and kind of mention in the report, and during post processing in the back of our mind we keep that okay, some of the TIAs are not accounted for, and depending on how significant they are, we might bump up or bump down the number a little bit later on at a later stage. Other checks. So in calibration, this is the last check we are going to discuss, and then we are going to discuss some methods for other checks as well. However, so far we are discussing the errors in the model. So like I mentioned in the beginning, the calibration step involves running the model and trying to figure out why the volumes are not matching, and then fixing the errors first. So far we are trying to fix the errors related to link speed, related to Centroids, related to Centroid connectors, now related to planned or coded projects, then coded land development projects, and this is the last one. We are trying to figure out the errors at other roadway network coding. In the next video, we will be looking more towards what to do after we have fixed the errors, like the kind of the general errors we can find. Then we do some deeper analysis to see what is going on in the model. So some other errors at the end of this video I want to mention is the other parameter that needs to be checked is the number of lanes. Believe it or not, the number of lanes are coded wrong in several times in a lot of transportation, a lot of TDMs. Functional class is another one to check for, and TAZ area type, which is dynamically defined. So depending on how the V lookup table is behaving, we might warrant a change in TAZ area type. However, changing the TAZ area type is kind of not recommended because the TDM model overrides the area type every time it runs. But we still do check for the area type on what was the area type in base year, what the area type is going to be in the future year. So these are some checks where if the functional class is wrong, we fix it. Number of lanes is wrong, we fix it. TAZ area type is wrong, we make a note of it. Any errors can be easily corrected by replacing the incorrect value with the correct value within TDM, except the area type, which gets overwritten every time the model initializes. The TDM calibration is mostly done by fixing model errors as described above. Several iterations may be needed to reduce the amount of errors in the model. However, not all errors can be addressed, and some errors may be more difficult to resolve than others because we are dealing with a very big data set with thousands of zones and tens of thousands of links. We cannot go and fix everything. Even within our small study area, even if we try to fix everything, there are always something off. So given that the TDM outputs are unreliable, understanding of how TDM works can greatly help to form engineering judgment while processing TDM output. So in the last video of this chapter, we will discuss the TDM output. So even though we cannot fix all the errors, or even let's not call it errors, let's say the TDM is behaving in certain way and in reality the counts are behaving in certain way, whether the TDM behavior is because of errors or because it's inherently what is algorithms are doing. Having an understanding of what TDM is doing and what the reality is will give us an edge when we are trying to post-process the TDM output. When we are trying to post-process the TDM output and we know what is TDM trying to do and what the reality is, then we can adjust our numbers in a way that we are more closer to where the reality needs to be. That's all for this video. In the next video, we will cover the second part of calibration, which is what we do after we have fixed all the errors and we are done playing with error checking. Then there are some deeper analysis we can do, and in the next video we will also see what would happen if we cannot calibrate a TDM model, which is not uncommon in many scenarios. No matter what we do, the TDM model cannot be calibrated, so we will see what to do in those scenarios.